Welcome to the already last lecture of this module. Today we talk about planets, moons, and explore a bit when could there be life. Well, for life usually we need liquid water and some kind of atmosphere. So we also have to look out where could we have, what are the conditions that a planet can hold an atmosphere, when is the atmosphere gone, or also that this atmosphere can have somehow water, especially liquid water. Okay, and one of my aims is, if you look tonight to the moon, that you say thank you. Oh, if in case it's possible to see the moon, of course. Scotland, what can we do? Okay, and what you see here in the first slide is a sketch with another solar system, a so-called TRAPPIST-1 system. TRAPPIST, well, for me as a friend of beer or beer drinker, TRAPPIST is this Belgian beer brewed by Belgian monks. Strictly spoken, from a German perspective, it's not a beer because it's often sugared against the purity law. And honestly, I don't like it because it's too hard. I don't like 11% beer. I think 5% that's enough. Okay, and it has been named well because the star was known before, but the system itself has been discovered by a group of the University of Liège. So, Belgian group, they named it a TRAPPIST. Probably they used the TRAPPIST for celebrating. And what they found is that around the red dwarf, only 40 light years away, so almost neighborhood, there is a solar system, or a couple of planets. And we see now body A in the solar system is the Sun. Then B, C, the planets are then basically given the alphabetic letters. So B, C, D, and here E, F, and G are in this green marked zone, which in our solar system, the Venus is just on the edge. Earth is perfectly suited, and Mars is almost on the edge to be outside. This is the so-called habitable zone, where liquid water exists. That means we are not too close to the star, that all the water is constantly evaporated. We are not too far away, that it's too cold, that not enough light comes along. And the water is constantly frozen. An ice world. So Star Wars, the second one, which is now the fifth one, with this battle on this ice planet. Okay, but now if we look at the sizes, well, the TRAPPIST system is in comparison to our solar system relatively small. It's a red dwarf, that means its gravity is very weak. Everything that was a bit further out is probably escaped. Then of course it's a red dwarf. It produces far, if you remember the Hertzsprung-Russell diagram, the luminosity on the y-axis, this was a log scale. It produces maybe a percent or so of the light of the sun. And then we have the 1 over r squared law. What means the habitable zone is much closer towards the central star. So we have now the condition liquid water, but in order to have water, every liquid has a vapor above its surface, and it's constantly exchanging particles with this vapor. And if we take the vapor away, what happens is the liquid still evaporates. It's of course the particles in the Maxwell-Boltzmann distribution that have the highest velocity and highest energy, and therefore we take the average energy of the gas is getting lower. We have collisions in the gas. This means the high energy tail is refilled. There might be again some evaporate, and at some point it's so cold it becomes solid, so ice. But if the vapor is taken away, we cool out down the liquid. By the way, we use this trick. If we bring something in thermal contact, we can cool it down. If we bring it in thermal contact with liquid helium, we can cool something down to 4 Kelvin. But the trick is now to take from the helium always the top layer away, or the vapor above, so that no gas molecules with a high velocity can dive into the liquid again and refill this high energy tail. We cool basically then down by always taking the high energy particles away. And with this trick we come down to, I think, a Kelvin or even a bit below. And then we need other tricks to cool further. Okay. And if you there are interested, Wolfgang Ketterle is the name at the MIT. Okay. So if a planet cannot host an atmosphere, this gas would be constantly taken away. Every liquid would become easily, even if it's in the habitable zone, it would become ice. And of course, if a planet loses atmosphere, it's anyway the stuff where the water is built up, or oxygen, nitrogen, that would be all gone at some point. And this is what we are now going to explore. So if you remember, or I introduced now these escape velocities. Because if a molecule has a velocity over this escape velocity, it has the chance to escape. Oh. And therefore it would be lost. The atmosphere of the planet becomes a bit thinner. And if this process happens constantly, given enough time, the atmosphere is gone. Okay. So let's again define this gravitational potential as the integral of the force along a way. And the way is of course away from the planet. Gravitational force works anyway in this direction. That's quite nice, so we can skip any vector conditions. Enter the gravitational force, integrate over r, we end with this kind of stuff. M would be then the mass of the Earth or of the planet, and this little m is the mass of the escaping body. What means we can now define basically this gravitational potential, and we would integrate in general from the surface, or where we start, maybe even a gas molecule in the upper layers of the atmosphere, the surface plus this height. And then this integral corresponds basically over force of the area that is enclosed by the force and 0, the x-axis. And we see now this height difference corresponds to a certain difference in energy that we need to invest to lift the particle from one height to another height. This is the energy. So integrating from the start value, what means surface or surface plus height, to infinity. Infinity means the particle is free. We end up with a relatively simple expression, the gravitational constant, the mass of the two bodies, and the starting value. And this is the potential energy. We set this equal to the kinetic energy, which is half times the mass multiplied with the velocity of the body. And then there is a velocity, or if this is equal to the potential energy, the particle has the potential to escape. If it's less, the particle will be bound. If it's more, clearly the particle can escape. That means we can now define a velocity, the escape velocity that is required for body of the mass m. That cancels away because we have it here, we have it here. To escape a body of the big mass capital M from a given height. This is our escape velocity. The minimum velocity a body needs to have to escape out of the gravitational field, otherwise it will be always bound. For example, the IS, the International Space Station, whatever it will become of it, we just let it crash because nobody wants to work with the Russians anymore. It's 400 kilometers high, it didn't escape the gravitational field of the Earth. So it's still bound. Okay, so this is a relatively simple expression, 2 times the gravitational constant multiplied with the mass divided by the distance of the star and the square root of it. Plugging in the mass of the Earth and the radius of the Earth, then we come down to 11.2 kilometers per second. Which is quite some speed. What corresponds in terms of 40,300 kilometers per hour. That means in 1 hour you're basically around the Earth. The equator of the Earth. Oh. For Mars, this becomes down because Mars is now much lighter and much smaller. These are effects that work against each other. So m over r. If the mass is less, so if we would have the same surface as the Earth, but only a third of the mass, then would be 1 over square root 3. That is then less. But it's both factors that play a role. Well, for Mars, from the surface, it's this 5 kilometers per second or 18,000 kilometers per hour. For Jupiter, well, we are 60.2 kilometers per second, but is of course still compared to the speed of light. Remember the escape velocity from a neutron star? 100 to 150,000 kilometers per hour. Per second, sorry. Half a third of the speed of light, or black hole, of course, it's 0 or infinite, so we can't escape. Per definition, well, 200, or in terms of Jupiter, we would need 216,720 kilometers per hour. So, this means also something. If we send a probe to Jupiter and want it to continue traveling, the problem is it's, of course, falling in this gravitational thing becomes faster. And then at some point it leaves again and becomes slower. The problem is, of course, we would like to have it as long as possible nearby this planet. It should be the other way around. It should stop down and then accelerate again when flying away. That's a bit of a pity, because then if you send a probe, space probe, to different planet with this slingshot method, the time you have to do actual experiments is usually very limited, because this is when it's fastest. Even a slingshot, I've seen that it accelerates like hell. It's but a bit of a problem, a bit of a nuisance. But we wanted to talk here about gas molecules. That means if we have no molecules that are faster than this here, goodbye molecule. And the atmosphere would constantly lose basically stuff. Why do we still have on Earth an atmosphere? Why does Venus have an atmosphere? Why does Mars has only an atmosphere of very big molecules? Bit true is the same as for Venus. She has a much denser atmosphere, but the molecules are usually heavier. It's carbon dioxide or heavier stuff than just N2 with 28 mass units, and carbon dioxide, well, 12 for the carbon, oxide 16, what means 3244. Much heavier in the terms of the mass, twice as much almost. So twice as bound gravitational. Okay. So the problem is now these Maxwell-Boltzmann distributions, which have always this tail, depending on a given temperature. And then if we have a certain escape kinetic energy or escape velocity for a molecule, they could escape. There's no way to hold them back at the moment. So the atmosphere would constantly lose density. Okay, then what do we now? If we go close to the sun, it's of course hotter. Hotter means more particles have on this high energy tail. So it's harder for a planet to keep an atmosphere. But we also learned already from this having the mass included, obviously a lighter planet has lower escape velocity and easier loses, and therefore cannot hold a too dense of an atmosphere. Things that we learned just by looking at this. Well, then we can look at the given a certain heat and therefore kinetic energy to the particles, how does, for given constant temperature, look the Maxwell-Boltzmann distributions of the individual gases. There enters also the mass. Then we see the heavier, the less do we have this tail. The lighter, the faster is the stuff, the easier it can escape. So if we split our water into hydrogen, that's it almost. Hydrogen is easily gone. Helium is easily gone. That's probably one of the reasons, despite that we have so much helium in the universe, we almost don't have some on Earth. It's very hard to find. It's in the atmosphere, but not too much of it. Oh. So what means lighter particles tend to escape easier? It means if you have heavier molecules, they tend more to stay in the atmosphere. Oh. Okay, so here, by the way, here's water, oxygen, nitrogen, carbon dioxide would be even more, a bit slower. So lighter particles easier tend to escape. Okay, where is it easiest to escape from? Near the surface of the Earth or the upper layers of the atmosphere? Of course, if you're on the upper layers, you need to, the escape velocity will be a bit lower. It's easier to escape. And for molecule to come up there, it undergoes a random walk. And there kicks something else in. Density, what means the number of molecules, is usually higher near the surface. And the higher you go, the less dense becomes the atmosphere. That is some kind of barometric formula. And of course it becomes a bit colder. Good effect. So if we talk about this stuff, it's rather the escape. The maximum Boltzmann distribution in the upper layer of the atmosphere. And then we also see that if we look at the height and the density, then we see, of course, this drastical decrease. We see that oxygen is decreasing faster because it's heavier. That's the reason why it was for a long time doubtful whether a human being could make it onto Mount Everest without additional oxygen, without having all these Nepalese guys that carry the super guy that makes the photograph all the stuff up. So if we have, so usually oxygen would be molecular, here it's then atomic, range is a bit on. Here it's even an ion. And this stuff is then usually, you see then, how the concentration of the lighter stuff is more in the upper layers. So if we would have water, it would be similar to this oxygen behaving because it's a similar mass. And then comes another effect in. What type of radiation is absorbed? Oh, here we have now basically rather first an amplifying effect. Of course, the lighter stuff that in a way easier tends to escape, tends to be on top. And then it will be, of course, refilled. Okay, and without, what does the atmosphere basically filter for us? Which part of the light? Almost all except the visible, but if we go to the harder side, UV light. UV light cracks molecules. And it's filtered by the atmosphere, what is good for us. But if it cracks molecules, if we have water on top of them, so in the upper layers, where we have a lot of UV light, the water is cracked. Then we have the free protons. And the free protons would immediately escape. The good thing is, they are usually the electrons, because the sour oxygen has more charges, it tends to keep more of the electrons. It tends to be the negatively charged ions, while the protons are positively charged ions. That might help us, because can we know these molecules or atoms, ions that try to escape, can we recycle them? So their velocity is so high, it's above the escape velocity. Usually they are on the run. Can we bring them back to the Alcatraz Earth for them? That we keep them. We want to have a stable conditions that our atmosphere has roughly the same density. Or that we are quite lucky because the Earth has this magnetic field. So a particle escapes somehow, and what happens? it travels out into space, but then the magnetic field makes it basically gyrate. It might be, if it's not super fast, it will be trapped by our magnetic field, the Earth's magnetic field. It gyrates around, and if it has a bit of a momentum along, either upwards or downwards, this field line, it will travel along this field line. And at some point, it's a spectrocycle into the atmosphere, where it might collide with another one, and then we keep it. Oof. And of course we get constantly this additional hydrogen by the sun. It's quite lucky for us. So thanks to our magnetic field, the Earth can keep an atmosphere. If we don't have this, the atmosphere would at least chemically change drastically. What we get constantly is also from the inner side of the Earth, from the inner parts, via volcanoes, a lot of stuff into our atmosphere. That helps to enrich. Of course, there the material is much more dense than on the surface would have. It's almost nothing compared to the solid stuff. What is the weight of 1 mole? Takes 22 liters of volume. 1 mole is in terms of oxygen 60 grams. What usually, if you have 60 grams of material, this is nothing. Okay, so it gets also refilled, but this is usually carbon dioxide. So we need something that would process this carbon dioxide, and the carbon is bound again and the oxygen is free for us. Plants, photosynthesis. Nice invention, otherwise, no. But if we don't have then this kind, we get more and more carbon dioxide, and the water might escape if there is no magnetic field. And then we get a carbon dioxide atmosphere, just like on Venus. Because the water escaped. But the heavier stuff stays there. Okay, so we are very lucky to have a magnetic field. So, why do we have a magnetic field? Because we have a molten core. But now let's go a bit through the planets. With this basically back in time, if a planet is too small, it cannot hold an atmosphere, or just a weak one. If it's close to the sun, the atmosphere gets so heated up. So, what would we expect for Mercury? Exactly, that's it. For Venus, I would expect a less denser atmosphere of very heavy molecules. Let's see. If she doesn't have a magnetic field, but this would indicate she doesn't have a core, a molten core. So again, so basically the solar system, the dictator, Mercury, Venus, Earth, Mars, the rocky planets, or the terrestrial planets, and then the 4 Jovian planets, Jupiter, Saturn, Uranus, Neptune. And then of course all these dwarf planets, so Ceres in the asteroid belt, but Ixion, Pluto, Orcus, Haumea, Quora, Varuna, Makey, Eris, Setna. Oh. So quite rich by now. And we go have now a look through. Of course this here is not to scale. If we would now plot the planets to scale, Earth is obviously on 1 astronomical unit, Neptune is on 30. Uranus is roughly 20, Saturn is at 10 astronomical units, Jupiter I think is 6 or 7. So basically the terrestrial planets are very in the inside. But they were formed on silicate, nickel, iron, rather heavier stuff. All the light stuff is the low melting point, is easy evaporated, it's gone. Especially no gases. Basically the Earth was formed just rock. And all we have as gas came then in the period of the early bombardment, so a couple of 100 million years after the formation, from dirty snowballs. That's where we got our water from. Thank you, comets. Oh. Of course, the same happened to Mars, Venus, and Mercury. We would expect, why are they no water worlds like ours? Well, of course, the radius, well, if you remember Kepler's law, the radius orbital period were related towards each other. So from directly, if we have this or this relative stuff, we could immediately have got just by observing how long does it take a planet to go once around the sun. And then we could have made this here, we just don't know the absolute scale. Okay, and the Habitable, and then we can take a look. Well, what is of course very important is the Habitable zone. This would be now for our solar system on top. Of course, Habitable zone, here the water boils off and here it's too cold and freezes. So we see Venus might be just, Mars might be just in, Jupiter is clearly out and Mercury is too close. There is no liquid water, it would be gases, but now Mercury is small. Well, we have the other solar system by now. We have, this is going to be for today the last video, how to find exoplanets. And what do we know so far? And one of the systems we have found is Gliese 581. There we have 4 planets, even some on the relatively seen, they would be called super Earths because twice as heavy. Means the gravity is a bit more than on our planet, but of course this also depends on the density and therefore on the volume, where are we relative towards the center. That also Earth-like planet, and this one of the super Earths is just in the habitable zone. Okay, and now let's basically go quickly through Mercury, Venus, so our inside planet, and of the gas giants where we possibly could find life. So clearly Mercury, well, Mercury, if I hear this I have to think of this guy. It was very, very impressive when I had the luck to see him live. But obviously this is astronomy, so let's stay with this guy. Nice photo of a Pathfinder, but I'm not sure which probe made this. Well, first of all, if you look at Mercury, it's relatively close to the Sun. Might be. So this is a log scale, unfortunately. Needs to be obviously Gliese 581 is again one of these dwarf stars. 20% of the mass of ours, or 30% only. So the Habitable, it emits far less light, and therefore we would have now to take a look in the Hertzsprung-Russell diagram, then we would see how much light it emits relative to our Sun. Therefore, habitable zone is much, much closer. So here is 90, 80, 70, so Venus 60, 50, so 35% of this 35% of the astronomical unit, so of the distance Earth-Sun, we find the Mercury, very close. So then the next thing is, if we look at it, it's relatively small compared to the Earth. it's small, it's close and hot, forget about any atmosphere. The particles can escape so easily, and it's constantly so hot that can't hold an atmosphere. Can't hold water, cannot have life. Bit boring. What is quite interesting, because it's so close to the sun, only the 30% of astronomical unit, and we know that the sun has a effects on the Earth. At latest, when you have moon and sun aligned, and then you get high tide, you usually get stuff flooded. Oh, and now for Mercury again, these tidal forces, they have the consequence that its rotation and revolution around the sun and its intrinsic rotation, they are locked. It has slowed down because it's a bit like the similar like for the moon with the Earth, that because the moon was much closer. We talk later about this. The gravitational forces were so strong that the moon has locked its rotation and revolution around the Earth. If you remember the very first lecture, these tidal forces, the same happened to Mercury, but in a different ratio. One day, what means one spin of Mercury is 58.5 days, roughly. And this is 2/3 of its year. It takes only 88 days, and it's once around the sun. With this information, you could immediately calculate now the relative size of its orbit towards Earth's orbit. And it had already this tidal locking, what means it's usually on one side, because it's now shown on quite a long time, very hot. And the other side is rather cool. It's like when you're in a campfire. When you are sitting too close, you get almost burned, and you go too far away, then it's a bit too cold, but then your back gets again cold, and so in campfire in the winter, of course. We all had this experience, poor Mercury. So a bit boring. The next planet is Venus. It's a bit too close to the sun. The atmosphere has lost almost all its water. Yet it's surprisingly dense. It's 92 bars, 96.5% carbon dioxide, or heavy molecule. With a relatively big escape velocity. Lots of carbon dioxide. What does this mean? Greenhouse effect. That had happened on Venus. It has about 200, 300, 400 degrees surface temperature. Then a lot of stuff that basically is also acidic. Not the best conditions for life. Maybe there are some organisms, but when should they have evolved from amino acids that immediately crack down? At least not life as we would know it. Of course, then we have seen it's special. It rotates the other way around, the wrong way around. One of the theories that might explain this is that if Mercury would be an escape moon of Venus, that would escape or explain the inverse rotation. Or that something came very relatively close during the formation. The push happened the other way around. Well, from the size, of course, why could the water escape? Well, we're going to see. It has a similar size than Earth, but its intrinsic structure is different. Its iron nickel core is solid. It doesn't have any magnetic field. We would explain the magnetic field on Earth with this convection current in the molten upper core of the Earth. Well, nice thing is it. If you don't have this, of course, nothing is shifted around the plates, but you have less tectonics, you don't get so much seismic activity. The only driver here is basically from the sun, the tidal forces. So this still allows for volcanism to be observed. So the volcanism explains this very dense, very active volcanism explains this very dense carbon dioxide atmosphere. But molten core means no magnetic field. No magnetic field means hydrogen goes away. No hydrogen, no water. Traces might be just explainable by the protons, hydrogen nuclei that are coming in from the sun. Well, what is quite interesting, of course, to look through this dense atmosphere. It has very dense clouds. We need radar. It's then hard to see something through. What most of you see here is that basically this sun, or the atmosphere. And if we want to look through, we need radar. So we needed to send a satellite with radar capability, and then we could nicely look through this at the surface. And what we find is that, for example, this Idun Mons. If we then have also infrared capability, we would see the heat. But this is clearly hotter, clear indication here is a volcano. Or a mountain that is hotter than its surrounding. That is at least what I would conclude. There must be a volcano. But this leads us now, why doesn't Venus has a molten core anymore? Similar size, it probably has the same amount of radioactive stuff that contributes to the heating of the core, but obviously not too much. And the biggest difference is we have a moon. In fact, our moon, so if we take a look at the moon in the solar system, not comprehensive. I think Jupiter has by now 30 or so. Saturn is also quite a large number. Of course, when they migrated inside, they might have caught a lot of bodies that already formed and kept them as moon, and in the common center of gravity moved them around. So that's an explanation why they have so much. Well, Uranus might have also, and well, Neptune also migrated a bit. Okay, Pluto has for its size, a relatively big moon like ours, but ours is really special. Comparing Jupiter, this massive gas monster, compared to our tiny, tiny terrestrial planet Earth, the moon is massive in the ratio. So compared to the Earth, there are bigger ones like Titan or Ganymede, Io, Callisto, the Jupiter moons here, and this one here from Saturn. But relative towards our size, this is immense. Therefore, well, if we look now at the Earth's moon, or the internal structure, a massive mantle compared to the Earth, so it cooled down already much more drastic. It has a solid but a slightly fluid outer core, partially molten core around. Interestingly, from the Apollo mission, we know that it has the same composition as the Earth. So it was not trapped or caught, built somewhere else in the solar system where there might be a different chemical composition. It must have been formed nearby the Earth or as part of the Earth. By the way, this was one of the most impressive things when last time I went to the US, I was having an experiment in North Carolina, but the flights to North Carolina were 2,000 pounds. I found then some for 400 pounds to Washington. And could then easily justify the additional cost of 250 pounds for a rental car, which I would have anyway taken in the US because otherwise you're completely stranded. And living for 2 weeks just off the gas station next to the hotel. Okay, so saved basically a lot by flying to Washington. There I went and before my flight was going I had basically morning time. So I went nearby the Capitol. There you have this avenue down to the monument, right hand side the White House, and there's loads of museums, and one is the Smithsonian Museum. If you ever come to Washington, go there. And one of the most impressive things in there was the moon rock. So you just see it, of course, you're not allowed to touch, but it's impressive. Okay, so what are the ideas? Why do we have such a big moon? There are a couple of theories, but I think the most likely one is that the young Earth, when it just basically formed, was still very hot and almost a liquid ball. It collided with a second planet and merged basically with the second planet, which is then called Theia. And the moon was built out. So, now the nice thing is, when it was built out, it was very, very close towards the Earth, only 20,000 kilometers above. But it was also faster rotating, and at some point, the tidal forces basically made it lock the rotation and the orbital movement. The intrinsic rotation and the orbital movement, so we see always the same sign. But in order to have this angular momentum conserved that was in this intrinsic rotation, the moon needed to migrate away to the place where it is now. And if you ever see this ice age where the comets impact, is it the comics or was it a scratch in the spaceship that made the solar system? There you see how the moon is relatively close, and you see this massive tidal force following the moon. Yeah. Well, did it matter if there were big floods on the land? No. Because the land was only settled about 700 million years ago. And why? Before, all the oxygen was bound mostly in water or carbon dioxide. There was no free oxygen. And every oxygen, plants come, invent this massive invention and super invention of photosynthesis and start producing oxygen. What does the oxygen do first? Well, if you have an older car, bring it to the MOT, what is the biggest fear? Rust. That everything is completely full with rust and parts that you can't see. Yeah. We had a lot of iron on the surface. And the iron was not also silicon. That was not, mostly not silicon dioxide or iron oxide. It was just iron. So it started oxiding. And this took about 3 billion years until there was then an atmosphere building up with oxygen. Then animal life could make it onto land because it had oxygen to breathe. Simple facts. Oh, but this young moon, or this theory, how it was basically do, please have here a look on this, stop this video and take it a look how this collision, how we imagine that it happened. So I think it starts at 0:45, so just please zoom in and enjoy it. And with this I would know it's already 52 minutes. Coffee is, oh, need another one. So enough for this video. Please zoom in for the next one where we go further to the next planet, Mars.